All right, let's get right into it. If you're in multivariable calculus, you've definitely run into the Jacobian. And yeah, at first glance, it looks pretty intimidating. But what if I told you it's actually just a superpowered version of a tool you already use all the time? Today, we're going to pull back the curtain and really understand the Jacobian. Think back to good old u substitution from Calc 1. Remember how when you swapped out dx for du, you had to stick in that little g prime of u term? Well, look at this. When we do the same kind of thing for double integrals, changing our variables, it's almost the exact same idea. Instead of a tiny length dx, we have a tiny area dA. And instead of that derivative, we have this mysterious new thing, the absolute value of j.
And that really is the million-dollar question, isn't it? What is this j even doing here? Why do we need it? And how on earth does it connect back to that simple little derivative we've known for ages? Well, that's exactly what we're about to figure out.
To really get the Jacobian, we've got to go back to its family roots. You can think of it as the big cousin to the derivative from u sub. But while that derivative was busy working on a one-dimensional line, the Jacobian is playing a much bigger game, with entire areas and volumes. Let's reframe something you already know. That g of u term wasn't just some random piece of algebra you had to memorize. No, it has a real job. It's a stretching factor. It tells you exactly how much a tiny little step in the u world, du, gets stretched out or shrunk down when you transform it into a step in the x world, dx. Okay, so if a simple derivative is the stretching factor for a line, it just makes sense that we need a more powerful tool to tell us how a tiny area gets stretched when we switch coordinate systems. And that tool, yep, you guessed it, is the Jacobian.
The Jacobian determinant is basically the multivariable answer to our stretching problem. See, when we change from xy coordinates to uv coordinates, a nice neat little square in the uv world gets warped. It gets stretched, twisted, maybe even rotated in the xy world. The Jacobian's whole job is to boil all that complexity down to a single number that tells us, hey, how much did the area change right at this spot?
So how do we find this magic number? We start by organizing everything into this handy little thing, the Jacobian matrix. Now don't let it scare you. It's just a table. It's super logical. The top row just tells us how x is changing as we wiggle u and v. And the bottom row, it tells us how y is changing. It's just a container for the four partial derivatives that describe the whole transformation.
And this right here is the whole point. To get our stretching factor j, we just find the determinant of that matrix. Now, geometrically, this is so cool. The determinant of a 2x2 matrix actually gives you the area of the little parallelogram that its columns make. And that is exactly the scaling factor we're looking for. We just slap an absolute value on it because, area can't be negative. And that's the number we plug into our integral. A tiny area du dv in our new simple world gets scaled up into the original area dA by this factor, j.
Okay, that's enough theory. Theory is great, but let's see this thing in action. We're going to calculate the Jacobian for a transformation you've probably used 100 times, maybe without even knowing why it works. Polar coordinates. The process is always the same, which is nice. It's a three-step recipe. First, you write down your transformation equations for x and y. Here, our new variables are r and theta. Second, you just systematically find those four partial derivatives and pop them into the 2x2 matrix. And third, you calculate the determinant. Just multiply the diagonals and subtract. Easy enough.
So we take all our partial derivatives, we plug them in, and we do the determinant calculation. You get cos theta times r cos theta minus negative r sine theta times sine theta. That all simplifies down to r cos squared theta plus r sine squared theta. And thanks to our old friend, the Pythagorean identity, that entire thing beautifully collapses down to just r.
And boom, there it is, the big aha moment. Every single time you've converted an integral to polar coordinates and just automatically wrote r dr d theta, you're using the Jacobian. That r isn't some magic fudge factor. It is the stretching factor. It's the precise number that tells you how a small rectangle in the r theta world gets transformed into a little wedge-shaped area in the xy world. How cool is that?
Okay, so that connection is really cool, for sure. But what is the Jacobian really for? Well, its true power, its whole purpose for existing, is to take integrals over really weird, nasty-looking regions and make them easy. Take this classic problem, finding the area of an ellipse. Trying to integrate over that shape directly is a nightmare. But watch this. We can make a clever transformation. Let's just say x equals au and y equals bv.
Suddenly, our ugly ellipse equation turns into u squared plus v squared less than or equal to 1, which is just a simple unit circle. The Jacobian for this is just the constant ab. So our area integral becomes ab times the double integral of 1 over a unit circle. Well, that integral is just the area of the circle, which is pi, and the answer is pi ab. Just elegant.
All right, let's kick it up a notch. Imagine trying to set up an integral over this region. It's this tilted diamond thing. To do it the old way, you'd have to split the integral into at least 2 different pieces, and the bounds of integration would be these messy linear equations. It's doable, but there has to be a better way.
And of course, there is. A smart transformation is the better way. If you look closely at the boundary lines, you'll see they have to do with y minus x and y plus x. So let's define our new variables that way. U equals y minus x and v equals y plus x. And just look at what happens. Our nightmare of a diamond in the xy plane becomes a perfect, beautiful, upright rectangle in the uv plane. The integration bounds are just simple numbers now. This is a game changer.
So we just followed the recipe again. We define u and v. We have to do a little algebra to solve for x and y so we can get our partials. We calculate the Jacobian, which turns out to be -1/2. We take the absolute value, so our stretching factor is just 1/2. And now that horrible original integral is replaced by a laughably simple one over a plain old rectangle. The hard problem has been completely transformed into an easy one.
So after all that, what's the big idea? When you walk away from this, what is the one thing you absolutely need to remember about the Jacobian?
Here it is. The Jacobian isn't just another formula to memorize. It's a strategy. It's a key that lets you choose your own battlefield. It lets you look at a problem with a really tough integration region, an ellipse, a tilted square, you name it, and say, nope, I'm going to transform you into a simple rectangle or a circle where I can actually do the integral. It is, fundamentally, a tool for making hard problems easy.
And that leaves us with one final thought to chew on. We've spent this time seeing how the 2x2 Jacobian tames wild areas. But this idea doesn't stop here. There's a 3x3 Jacobian for triple integrals that tames wild volumes. In fact, it's the reason we have those extra terms in cylindrical and spherical coordinates. So the question to leave you with is, now that you have this key, what other complex 3D shapes could you unlock next?